All right, so hello everybody, and welcome to our final workshop. This is the last workshop of the quarter, and also the last workshop with Jackie and I as your workshop's co-leads. So we've very much enjoyed being workshop leads this year, and we hope you've enjoyed our workshops. David and Sadat being awesome workshop leads next year. So today's topic is going to be on machine learning, which is kind of a big one. It was much requested, and it's a big buzzword in today's day and age. So let's first talk about what exactly it is. So machine learning in general can be considered as a type of artificial intelligence. Once again, another big buzzword. And what it does is it allows computers to do a task without being explicitly programmed to do that task. So they can learn it by themselves, sort of. And without knowing it, you've probably encountered lots of machine learning in your everyday life. One aspect might be identifying spam emails. And sometimes ways computers can do that is by noticing if there is an email address that seems really strange, like a random assortment of letters or something like that. And also it can learn from your behavior. For instance, if there is a particular address that's been sending you mail and you keep on moving those emails into the junk folder, then it can start to realize, hey, this is junk, and move it there. And this happens without you explicitly programming that, which is pretty cool. And another way you've probably been exposed to it is product recommendations. I think we've all shopped on Amazon or eBay, and you'll notice that after you click on certain products or buy them, they'll show up in recommended listings. And this even goes further on the internet. For instance, I am a musician, so oftentimes I'll buy guitar pedals or strings online. And now I can't go anywhere on any websites with ads without getting ads for musical products, like Fender or Musician Friend, Sweetwater, all that kind of stuff. So that's another way. And then a third kind of machine learning that we might have encountered is image recognition. And this is pretty cool because it's a way that our computers can distinguish between different kinds of images. For instance, it can distinguish between an animal or a flower, or even different kinds of flowers or different kinds of animals. So these are just a bunch of different ways that machine learning can be used in our everyday lives. So there's a couple different categories of machine learning that we can talk about, and those are classification versus prediction problems. So classification is, like we just mentioned, with those different kinds of images. It's identifying the category or class of a particular object. It can be an image or a different kind of product. So that's one kind. And then another kind that we could think about is prediction. And so this takes a certain amount of data that you give it, and then it makes a model, and based on that, it can identify future information that you give it to create a correct output based on that input. So when we're deciding on our machine learning model, we want to decide whether or not we're dealing with a classification or a prediction problem before we create that model. And you can see on the right, oftentimes prediction models are done with regression. And if we've taken complicated math classes, which I've assumed we all have, you'll remember things like linear regression or even quadratic regression, which is making a function that will model based on data points that you're given. And so that's oftentimes how prediction problems are done. All right, so let's see an example of one of the most important parts of your machine learning model, which is it all starts with data. So you can see right here that we've got a bunch of features which make up our data. And for the most part in this particular list, they're the same. Like these are all different developers. They all have the same skill level, same country, and same city. But you can see that they vary in experience. And this is a type of machine learning problem that based on this data will determine what the output is, or the label, the salary is, based on these given inputs. So that's a term that we haven't talked about before, but it's important. And label is basically what's sometimes called the ground truth, which means the output that is applicable to a certain amount of input data. And so that's just a vocabulary word that we're going to need to talk about. So can anybody tell me whether this problem right here, we would consider it as a classification or a regression kind of problem? You can either type it in the chat or just speak up. Got a 50-50% chance of being right. So just give your best guess. All right, very nice. Yes, this is a regression problem. It's one easy way to think about that is we're dealing with numbers. So that's probably a little bit of a tip off right out of the way, but we can see that we've got an increasing experience, and then associated with that is an increasing salary. So yes, that's it. All right. So next, this would be, of course, an example of a classification system, because we're saying we want to classify the dog's breed. But can anybody identify some of the features that we would need to think about if we were trying to classify a dog's breed based on its picture? This is also a fun exercise. Size, ears, yeah, that's all true. We want ways to distinguish between each of these pictures. So we can see that, for instance, one of the dogs has long pointy ears, one has long floppy ears, one has short floppy ears, and one has shortish pointy ears. Fluffiness could also be one, depending on how fluffy the different dog breeds are. And we could distinguish by color too. That's something we have a capability of doing. So there's lots of different features we can identify when we're doing classifications. So I mentioned data before when we were talking about that feature set in an earlier slide. So machine learning starts with data. That's how you build your model, and that's how you test it. It's all about data. So once you get a data set and you're going to think about constructing your model, what you want to do first is split it up a little bit. And you're going to split it. One way to do that is an 80-20 split. And this means that you take 80% of that data and you put it in a set that you're going to use for training your model. And this will be like fine-tuning the parameters. We'll talk a little bit more about that later. And then the rest will be in a test set, and you're going to sort of set that aside and run it through your model at the end, just to make sure that your model is working pretty correctly. So I think one of the reasons that one thing that's important to talk about with this is that we are allocating a lot more data to training than testing. And this is because we really want our model to be solid. So the more data we give that, the better. All right, so once we have our model made, and once again, we'll talk about that a little bit more later, what we want to do to evaluate whether it's good or not is to talk about its error. And we can do that by looking at a couple things called loss functions. So the ways of looking at error are, one of them is mean absolute error, or MAE. So how you calculate this is that you just sum all the differences between what your model predicts an output will be and what the actual output or label is. So you're checking your ground truth against what your model actually gives out. And then after that, you divide that sum by the total number of test data samples. And so this just gives a really good idea of how much error there is per point or per output in your model. And another way to do this, which is very slightly different, is the mean squared error. So as you might expect by the name, all you want to do here is you're going to square that difference that you calculate before summing. So you're just going to get a sum of all the squares, which you're going to divide by the total number once again. So these are just two important ideas to have in mind when you're testing your model to make sure that it performs decently. And if the numbers you're getting aren't good, you might have to rethink your model. So there's a couple of problems that we can run into, and one of these is overfitting. This is something that you might not actually think would be a problem, which is that your model fits your data too well. And at first, that might not seem like an issue, but if it fits your training data too well, that could mean that it's not going to be generalized enough. And this is a great example over here on the right. We've got a polynomial that fits all the points on our plot very well, but you can see that it's not tracking any sort of trend. It gets close to all the points, but it's going to kind of go down at the end, which is not likely what we're looking for. We can see this kind of has a trend where it's going upwards, although the rate at which it's going upwards is slowing down. So this is an example of overfitting, because if we go to points that are outside this data set, it's probably not going to fit particularly well. So basically a way of summarizing this is that it doesn't generalize well over points not in the training data set. So the opposite problem to this, and one that you probably thought about that could be a problem, is underfitting. And this is when your model just isn't complex enough. So we can see right here that we've gone to the total opposite extreme. Rather than having a large polynomial to fit our data, what we've gotten right here is just simply a linear model. And while it does go through the data points, we can see that at the end especially, its slope is going to be way too high for what we're looking at. So it's not going to generalize well outside of the scope of our training data once again. So this generalizes too much rather than too little like before. So what we're going to be looking at, we're looking for, is something that's somewhere between these two. And that is our Goldilocks mode, with our just right position, which we can see right here. For this particular model, it's very simple. It's just a quadratic fit right here. And it fits all the test points well, but we can see particularly that it fits the trend where the test points are going. Which is perfect. It's exactly what we're looking for. And you can see sort of on the graph on the right there, there's a sweet spot between underfitting and overfitting. where you reach that ideal complexity of your model. And that's what we try to go for when we're doing machine learning. So you might be wondering how we prevent overfitting and how we make sure our model is good, how we make sure it's not too specific to any one data set. And one method for doing that is called KFold Crossvalidation. And so this sort of eliminates the possibility that there's chance in why our training data is performing well with some of the testing data. And we sort of do this by mixing up which data we're using for training. So how we do this is we take that training data set that we first used on the model, and then we break it up once again. And we can break it up into k different parts. In our example on the right, we've just broken it up into 5 again, so we can sort of mimic that 80-20 kind of form that we talked about before. But so what we do is we take 4 of those 5, or k minus 1 of those k sets, and then we perform training on those k minus 1 sets. And then after we're done with this, what we do is we rotate it. So we put that validation fold back into the training folds and then rotate out one of the training folds. And then we rotate this k times until all of the different blocks have been our validation fold. So we've gotten all the different combinations. And what this is going to do is it's going to make sure our training model is valid. So this is just a good technique to use to make sure that everything is kosher in our model. Another couple things to talk about in machine learning are different kinds of learning, and those are supervised versus unsupervised learning. So the kinds that we've been mostly talking about so far have been supervised. And what this basically means is that the set of data that you're given has associated with it some output for each of the input sets. And that's like we were seeing before, the set of data with the software developers and their salaries, the salaries were already given in your data. So this is supervised because we know what the ground truth should be for our training and testing data. Now, unsupervised data, on the other hand, is when we are given data sets that do not have those labels, or do not have those ground truths associated with them. And so this can be a little bit more challenging sometimes. So can anybody think of any examples of supervised and unsupervised data sets that we might get? Anything's fine. Just put it in the chat if you can. All right, I'm going to wait another 10 seconds or so, and then I'll just give you guys a couple examples because it can be kind of difficult to think of. Dog breed supervised? Yes, exactly. Yeah, because we know what all the dog breeds are before. We just want to make sure our training system associates the correct ones with the correct ones. So yes, very nice. But some examples of unsupervised ones, for instance, could be say that you want to look through your emails and collect all of them that are on a certain topic. And the set of emails that you have, there's no prior set of labels for that. So you could just make an algorithm that would look through your emails and then would associate them based on certain words or whatever, and you don't have any labels for that. So that could be an example of some unsupervised learning. All right, so let's talk about some different models that we can use now. This is actually the nitty-gritty of machine learning. We've sort of been talking about topics up to this point. So a couple models are, one of them is decision trees. And so I'm sure people have seen these before, but this sort of goes down from the top and based on the option that is chosen or based on one of the attributes of the data that we're given, it will move either left, down, or right, or in however many directions we need to move to get to the right area. So this is a supervised learning algorithm, and it can solve both regression and classification problems. So as we can see up above, each internal node represents a decision that you have to make. So you can think of it as a topic, and then there are 3 different sub-decisions for it. And depending on which one you choose, you move to a different part of the decision tree. And once you reach a leaf node at the bottom of the tree, that means that you've made a final decision. So we can just look at how that looks like on the right. And this is a decision tree for whether or not somebody wants to play badminton. So if the weather is rainy, then you go and check if it's windy. And if it is strongly windy and rainy, you probably don't want to play badminton. If you've ever tried playing badminton in the wind, it doesn't go so well. On the other hand, if it's sunny and normal, then you're probably going to want to play badminton, because who wouldn't want to? So you can see that this leads us to different decisions based on different attributes of the day. Now, another model that we can use is linear regression, and this will take the form of a simple function. Sometimes y equals mx plus b. I guess that is linear regression, but there's also things like quadratic regression and higher polynomial regression, as we've seen a little bit earlier on. So there's some different models that we can use when we want to make our machine learning algorithm. So let's summarize all that by going through the whole machine learning process and looking at all of its steps. So the first one, as I mentioned before, is data collection. That's where we get started with, and that's how we test everything. It's just the basis of our entire idea of machine learning. So once we have all of our data, and of course we want to have as much of it as we can, what we want to do is prepare that data. So if anybody's taken things like 4AL or 4BL at UCLA, you'll know that when you take data sets, there's oftentimes random errors, and that can be just errors in the machinery or errors if you moved your hand during some of the data. So we kind of want to get rid of some of that. Also, if there's duplicates in the data, we don't really need to pass that through our training or our testing, because we don't need to do that more than once. And sometimes data can be not normalized to the extent that we want it to, or not in the right units, and so we want to change that. So we're just basically prepping all of the data, and then after we've done that, we can split it into our 80-20 split, like we mentioned before. So some of it will be for training, and some will be for testing. So at this point, we've got all of our data prepared, and so we can go to the next step, and that's choosing our model. And we mentioned a few of these earlier in the lecture. So different algorithms are going to be used for different tasks, and we'll want to think about what we're doing. Are we classifying, like with dogs? Are we predicting? Do we want some sort of regression for that, and so on. So once we've chosen our model, then we want to train it, and this involves feeding our training data into the model. If it's supervised, then what we do is we compare the output that we get with the output that we already know with the labels that we know. So that's the training step. Now, after we train it, then we want to evaluate the model. And we talked about how we calculate the different errors for this. And if we've got a lot of error, then we know that there's something wrong with it. And maybe we have to go back, choose a different model, or vary our parameters and so on. So that kind of involves the next step. And that is parameter tuning. So there's lots of parameters for a model that can be changed. And those can be like the amount of steps that each training round goes through, the learning rate of your model, and what the different nodes in your model are initialized to. And so those are all things that you might have to change or tweak, especially if you get an error that's beyond what you were looking for in the beginning. And finally, after that, what we want to do is use our testing data that we set aside at the beginning. We feed it into the model, simulate how it'll perform in the real world. And once again, if we've got supervised data, this is super easy because we can just compare it with the outputs we already know. And so this is basically our whole machine learning process. So I think our next bit is we're going to get into is Jackie with the IMU gesture recognition project. This is really cool.
I think there is a question from the Amazon gift card. Let me just update this real quick. Sorry about that. Oh, okay, just kidding. Let me share my screen.
Yes.
Okay. So for the $5 Amazon gift card, the first person to thoroughly explain the entire process of like the KFold cross-validation and maybe why we need to use it will get the gift card, but yes. So type it in the chat and then we'll decide from there.
Type in the chat, thoroughness is appreciated. So I guess while we're doing that, quick anecdote right here. So another type of machine learning that we didn't mention is like a neural network machine learning, which sort of is modeled after the human brain and has nodes with different values that are changed during training. And so that was actually one of the first kinds of machine learning that was explored like in the 70s. And then at a certain point, they just gave up because they didn't have the computing capacity to actually make that useful at that point. And then for years and years, they just focused on other more mathematical kinds. And it was actually around 2012 that somebody looked back and thought, hey, this might be a good idea to try again now that we've got more computing power. And so that's been one of the biggest areas of machine learning actually in the last 8 or so years. And part of the reason it's become such a big buzzword recently.
Thank you for sharing, Travis. We'll just wait like a couple of minutes for people to type in chat. And then we'll move on to the Kahoot right after. All right, thank you, Erica. Is there anyone else that has an answer as well? And sadly, David won't be entered in the raffle for the Amazon gift card because Erica explained it first. All right, so the Amazon gift card will go to Erica, and we're going to start our Kahoot for the next Amazon gift card. Let's see. Play. Okay, so the game pin is going to be 6687610. And we're just gonna wait a little bit for people to join. We have Chadster.
Preston's not here, so it's anybody's game.
That's very true. We have Juan. Oh, so sweet. I'm assuming David is J Park my car.
I mean, it could also be Shay.
That's true.
Oh, appreciate it.
I think there's like 3 more people, I believe. So wait 1 more second for them.
Erica wants both Amazon gift cards today.
You'll have $10. Okay, I'm starting in 5, 4, 3, 2, 1. So first question is going to be, what is a classification model? So the output can be any number and has a continuous range. Output only has a finite amount of predefined labels / classes. Every classification model only has 2 outputs, and every classification model's output has to be a number. So which one is true of the following about a classification model? Yes. So there's only a limited amount of predefined outputs for classification, hence the name classifying. And every classification model does not actually have to be a number. It can be like different categories like dog breeds. So it doesn't have to be a numeric value. So we have Jay parked my car, then Chadster and Chadsterious Hole. I don't know which one's actually Chester, but they're competing. What model did we learn today that will help us classify IMU gestures? Either the regression model or decision tree. Yeah, so the decision tree, the regression model will give it like how we saw in the graphs of the different models, like quadratic or linear regressions. Those are like actual numeric values, but with these IMU gestures, we kind of want to just categorize them using our decision tree. So Chadster moved up to first place, followed by Jay and Chadsterious Hole. True or false, a label is represented by a single column output. It is true. Remember, label is kind of just like our output, and we should only have one column for each feature row. So we still have Chadster at the top, then we have I Love Jackie and Achinthia in third. True or false, there can be multiple features, and a feature is considered an input to the model. Awesome job, everyone got that right. And the top three still remain the same. What is a typical ratio to split data into train test sets? And notice train is first and test is second. So 20/80, 30/70, 70/30, or 80/20. Yes, it is 80/20. We typically want the training set to have a larger ratio than our test. And so what is true about loss functions? Tells you how much you lost in Bitcoin because of Elon Musk. We typically want a higher value as output for our loss function, compares the actual and predicted values of model to determine performance, or it's not actually that useful. Awesome, everyone got that as well. And so Cynthia moved up to second. And what is not true about overfitting? Model fits the training data too well and performs poorly, and test data usually occurs with lower degree polynomials, usually occurs with higher degree polynomials, and this occurs when Travis works out too much. So what is not true? Yeah, so it usually occurs with lower degree polynomials is not true. And so what is not true about underfitting? Sorry, I spelled that wrong as well. Performs poorly in both training and testing data. Model isn't complex enough to capture relationship between input and output, occurs when I don't work out enough, or model fits too closely to training data. Awesome job. So underfitting is like overgeneralizing, and that's why we actually do not fit to our training data. So we still have Jay, Chadster, and Achinthia. True or false, unsupervised learning means the model is trained using training data set with given labels, aka correct predictions. So this is unsupervised learning. Awesome job. And let's see who's at the top. So in third place, we have Achinthia, then we have Chadster, and in first place, we have J Park My Car. So I'm not really sure who J Park My Car is unless it's actually J. But please like let me know in the chat so I can give it to the Amazon gift card to the right person. Oh, so it actually was David Cow. Okay.
Solid 80% sure that it's actually Jay, but I guess we can just determine this later.
Oh.
Wait, it is David? Okay, never mind, it's David.
Oh, it is. Okay, so it is David. I need to rewrite this so I don't forget. And then I'll send you the code after the workshop. And let's go back to our slides. I'll exit this. Okay, so now onto our hands-on component. This is basically kind of adding on to what we did last workshop where we used the IMU and the Arduino to collect the IMU values, which is like the X, Y, and Z directions. And so I'm not gonna go like too much into like the IMU again, but just know, just like an overall view, it's made of a gyroscope and accelerometer. The gyroscope typically tells you the orientation or angle in like the X, Y, Z direction. So if you tilt it like in those different axes, that's what the gyroscope will help give. And then accelerometer is the direction in the axis you are moving like your IMU in. So as you can see over here, if you move upward, you're going to move towards the Z axis, and then same thing with Y and X. And that's why we say like our IMU has 6 degrees of freedom. And then wiring the IMU up, you should also have this pretty much from last week. We didn't really change anything, but let me know in the chat if you don't have it right now. Or actually let me know if you do have it already wired up. So it should look like, I have like another account that has my video feed of like the Arduino and like how it should be wired up. So please let me know if you have any trouble. Okay, I will move on then if no one else has any problems. Okay, so this is basically what we're going to do in our IMU gesture classification. The first thing we need to do is basically collect our data from the IMU. So in our Arduino IDE, we're going to print out the values of the IMU and then save those values into a CSV file. And each CSV file will basically be for a new gesture. So today we're just going to have 3 gestures to make it pretty simple and basic. And in each row of your CSV file, it should be 1 sample of that same gesture. Then we move on to data preparation. We're just going to repeat about 10 samples for each gesture or CSV files, just to account for like any noise we might encounter just by like, and we don't want to just only do 1 gesture 1 time. Then after that, we're going to choose a model. In this example or demo, we'll use a random forest classifier in Python, which is just an average of like a bunch of decision trees. And this will help prevent like overfitting by using like an ensemble of decision trees. Then we're going to train the model in our Google Colab environment. So you don't need to install Python like yourself or any other like external IDEs. And we're going to basically take the CSV files that contains the gesture training data from our Arduino to use as our training data for our random forest classifier. Then finally, we'll just evaluate our model. And right before we do that, we want to convert the model, which is in Python in our Google Colab environment, to C code and then transfer it back to a new Arduino program. Then we'll just test our model by trying out each gesture and seeing if the output is actually what we expect. And right now it's like probably a little bit confusing, but it will be a lot easier once we walk through together what we need to do. Okay. And then, sorry, this was just a repetition of the previous slide. First, we're just going to collect our data using our IMU in the Arduino program. And then, sorry, we already answered this in our Kahoot. This will be basically a classification problem to classify various IMU gestures. And so here's just basically like 3 files that we'll need. We need one Arduino program where we collect our training data and put each gesture into a different file. And for each gesture or CSV file, we'll do that for 10 times. Then we'll move on to our Google Colab environment where we'll write some Python code to essentially use that training data, put it into our random forest model, and then convert it to C code so that our Arduino can understand. And then finally, we'll write another Arduino program, which will load that converted model and then start testing the classification of various gestures. So if you can download the zip file from this folder right here, that would be awesome. And what that will contain are basically these 3 folders and this file right here. So the first folder called ML Collect Training New folder, it's just the Arduino program to collect the IMU training data. Then we have the ML Testing new folder, which just contains the Arduino program with our converted model. We'll update this later on because everyone has different training data to essentially classify features, but this is just an example for now. And then we have another folder called Dataset new, and this will contain the 3 CSV files whose data you actually need to change with your own gesture data. And then finally, we have model generator dot IPYNB file. And so this is also known as like a Jupyter Notebook file, but you can also run all the Jupyter Notebook files in Google Colab, so you don't actually need to install Jupyter Notebook. And then this is what we're going to use to convert our model. So once you're done with that, we're going to start off with what we mentioned before to just collect all of our IMU samples. And oh, thank you, Caleb, for posting that in the chat. So once we run that Arduino program, we're going to see this in the very first line. It's just saying calibrated X, calibrated Y, and calibrated Z, which are just our initial IMU XYZ values that were like average over 100 samples at the beginning of the program, just to eliminate like any noise you might encounter. And then each line after that represents one sample of a gesture for basically the same gesture you're doing. So if I'm doing like the motion of moving my IMU or tilting it forward, then the acceleration threshold will be triggered, and this line of output will be printed to your serial monitor. And so in this case, the format is basically IMU X, IMU Y, IMU Z, and that's repeated on the same line. And then once you make another gesture, that's going to print out another line, and so on. And so after you do 10 samples of this, you want to copy and paste everything excluding the first line, which is like the calibrated line, into a CSV file called whatever the gesture name you want, .csv, and then move that file into our dataset new folder. Then we want to just repeat the same process for our two other gestures. And I'm going to do a quick demo right now. I'm going to stop sharing really quickly and then share my Arduino screen. Sorry about that. Okay. Do you see a screen with like the Arduino IDE there? Okay, thank you so much, Travis. And so let's see if I open up my serial monitor. Sorry, this was like a previous output. Let me just clear it again. And then can you also see my Arduino as well, Travis? Oops, sorry, I actually triggered it.
Yes, I can see it.
Okay, perfect. So if possible, please try to follow like both like looking at the screen and the video feed of my Arduino at the same time. Okay, so I just reset everything and then it's going to run again and output these calibrated values. What this means is just like at rest, our IMU X value 0, our IMU Y value 0, and our IMU Z values at 99. And so every time I make like a different gesture, it should output a row of values. And so if I go, for this time, I'm just going to tilt it forward. And so an acceleration threshold is basically triggered, and that's output to our serial monitor. And if we look through our code here, in void setup, we just set up the IMU so it can communicate using I2C, and then calibrate basically calibrates the IMU X, Y, and Z values, as we can see down here. And that's where we print it out to our serial monitor. You don't need to know like the very exact details of like every single step of the code, but I will give like a high level overview of what each part does. And if you have any questions, like feel free to ask after the workshop. And then within our loop, void loop function, we essentially want to call IMU loop so that the variables IMU X, Y, and Z can be updated at each call. And then we first detect, and then we detect if motion, if there has been a motion that's triggered, and if not, we return to the beginning of the loop. If not, and a motion actually has been detected, we want to record the IMU values, which is all of this inside the array that we declared at the top. So if we go into record IMU, we see that we go through a certain number of samples that we defined previously. We call IMU loop, so we can extract those different IMU values and then update the features array with the acceleration X, acceleration Y, and acceleration Z values. Then once we're done with that, we actually just print that entire array to our serial monitor. As we can see in here, all we do is just loop through the array and print to the serial monitor. And then finally, we want to reset everything by detecting if we're just going to keep going through this while loop until our threshold isn't triggered anymore, because we don't want those values to be carried on to the next gesture sample. And just like everything is just at rest, essentially, when we reset. And so I'm gonna do this 9 more times because I already have like 1 sample. So I'm gonna move forward. And then this is my 3rd time, 4th time, 5th time, 6th time, 7th time, 8th time, 9th time. Oh, and then, sorry, this was accidentally triggered at the end, and then 10th time. So I will copy all of this. I'm gonna get this like second to last line out because it's not actually, that was like an accidental trigger. And then I will copy and paste this into a CSV file. Okay, so I already have it like in my folder. So this is what it will basically look like after you unzip your folder, and you'll see dataset new. I'm just going to open 4.csv and replace everything. Okay. And then this was the value that I did not want. Okay. And then I'm gonna do that for like a backwards motion and then like a right tilt motion as well. So I'm going to go back here. I'm going to clear the output and then reset the program. And then do it once more. So in this case, I'm going to do a backwards motion. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Oh, okay, so that last one was triggered. So I'm going to copy the first 10 samples of this and then change this backward.csv file and then input my own data. And then save that, and then I'll exit at that. And then let's do this one last time for a 3rd gesture. I'm going to clear the output and then reset the program, wait for the calibrated line to appear, and then that means I'm ready to do my gestures again. So I'm just going to tilt it to the right. So this is 1, 2. Oops. Oh, sorry, unplugged my Arduino. Sorry, I'll reset this one more time. Okay, so I think something happened. I'm just gonna upload this back onto my Arduino. And then if there's any questions, okay. Caleb said, is the current data in the CSV files valid? Yeah. So those are just kind of like what I did like myself, but like everyone kind of has like a different like motion that will probably work better with you. But I think it could still work. Okay. So now I'm gonna go. Okay. 1. I'm sorry. It keeps accidentally triggering. Please bear with me. Okay. 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so there's like some numbers in here that were accidentally triggered or sampled. So I'll just take this one, and this one out, and then redo one more time. Also, Travis, is there anything else in the chat?
Clean.
Okay. Then I'll go back to right. And then, so I'll just like show you how like this is already valid, but you just copy and paste this from our previous time. I didn't do a great job this time, but like before the workshop, I did a good job. And so I'll just use this data. And then let's go back to our slides and see what we need to do. Okay. So we already did that for our 2 gestures. And then in your Google, you should have this in your Google Drive. So you want to re-upload your 3 CSV values into dataset new, because we'll have to use this like directory or these files in your Google Colab environment, and that's how it will work. And so here's just like an example of how like 4.csv might look like, but these like numbers don't have to be exact. And then let's go continue. Okay, so now we're going to use the model generator Jupyter Notebook file in Google Colab. So what you basically, and this is how it will look like when you open it up. And what you need to do is first double click on this file in Google Drive. So just double click this right here, and it'll automatically take you to your Google Colab environment. And then within the code, there's just like 4 or 5 cells. The first one is to install this library, which just helps us convert our Python models to C code. Then we need to allow Google Colab to access our Google Drive, and then essentially access our CSV files. And then we want to create our random forest model using the CSV file as a training data, and then also using the sklearn library to do that. And then finally, once we're done, we'll copy the output of the cell with the converted C code. And then let me just exit out of this and go back over here. So yeah, so if you see like, if you go into my drive and then somehow like create your own folder, ML workshop or whatever you want to name this, you'll see the Jupyter Notebook file right here. I'll double click that. And then it should pull this up. It'll take like a little bit to load. And then, yeah, so this is what I said in the beginning. You use like exclamation point pip install, and then this library that we will need to convert to C code. So I'm just going to execute that just by clicking on this like little play button, and it's to the cell. You can also do like command enter, I think, if you have a Mac. And so I already downloaded it before, so it just says requirement already satisfied. Then this is how you're going to grant access to our Google Colab environment, to our Google Drive. So we just run this, and then it says drive already mounted, but typically it would take you to like another authorization link, and then it would ask you to just copy and paste like a token in it, and then it will just automatically authorize you from there. And then once you're done with that, there's a function called load features, which just takes in basically a folder path. And in our case, we want to use our dataset folder because that contains all of our CSV values. And then this basically formats all of that so that they're interpreted as features for our model that will run in our next cell. So I'll run this. And then after that's run, I move on over here. And so as you can see, we're importing the random forest classifier from our sklearn library, as well as from our micro MLgen library as well. So in the beginning, we identify like our features and class map as the return value of our load features function. And so this might be different for everyone else. However, everything is prefixed with content. I have G drive and then my drive in the beginning. And then whatever folder you have your Python or like Jupyter Notebook file in, you want to append that to the rest of this path. So in our case, I have ML workshop and then dataset new. So my drive, ML workshop, and then I have dataset new, which has all my CSV files. And then does that make sense so far? Can I get like thumbs up? I can't really see anyone, so I'll need Travis to let me know.
I'm seeing some thumbs up. Looks good.
Okay, awesome. I like seeing these thumbs. Okay, now we create our random forest classifier, and then we say we want basically 30 decision trees to basically average out into a single random forest classifier. We specify the max depth of our decision tree as 10. And these are all like parameters that you can play around with yourself and tune just to see like, oh, would this give me a better model or not? And then we want to fit it to our X, Y variables. And so our X is basically our features, all of our input, and then Y is our single column output. And all of that is basically done using our like load features function. So you don't have to like worry about like manually doing that yourself. And then we finally convert it into C code using this port function, which takes in our classifier and then just declaring our class map to be this. And our class map basically says it maps like the values 0, which is like, these are like our outputs to our backward gesture, 1 to our forward, and then 2 to our right gesture. And so after I run this, you should get this like huge like output of like C code. And as you can see, there's like a lot of like if else statements. So this is like telling you all the trees. We have like tree 4, and it should go, and it goes all the way to tree 30. And this is probably kind of like why people say like, oh, machine learning is just like a bunch of if else statements. And like, in a way it is, like if you have like a decision tree classifier, but what you want to do is copy all of this. Oh gosh. Copy all of that output. And then we want to open up I'm going to exit this for now because we don't need it. And then we're going to open up the ML testing new Arduino program. You can see that we have a file called model.h, and you essentially just want to copy and paste everything into here. And we want to remove this like include CSTDR because I believe that will give us like a compilation error and we don't really need it. So if I see that, and yeah, so it just says no file directory, but we don't actually need this. It's like just extra. So I'm going to upload this to the Arduino right now. And then we can see like our 3 different gestures that we have. And then I'll go into our code. It's like pretty similar to what we had when we were collecting the values for training. But essentially we do like we just set up IMU and then calibrate the X, Y, Z values. and then detect if motion has been detected. If not, we just go back to the beginning of the loop. Then we record the IMU values as we do them. And instead of actually printing them out to our serial monitor, we want to pass this to our classification model. And so in classify, it basically takes our model from model.h, and then it'll help output the right value that we want. So that's why it says like predicted class, and then it will say classifier.predict label, and then given the features that we had for that particular input of like when the user tilted like the IMU. And then we'll see that right now. I think I uploaded this, but I'm gonna just do it again. Gosh. Okay, sorry, I want to just unplug this and plug it back in. I feel like things always go wrong when I'm presenting.
Windows are so fidgety.
Yeah. This upload's taking long. Okay. Okay, we got it. So yeah, print out the calibrated values again. And then once you see that, you can do your first gesture. So I hope this works. Sometimes it's not like super accurate, which is like thing about like machine learning models. So I'll do my best to redo the gestures correctly. So I'm going to do the forward one. And then that's our predicted class. And then once you see do gesture again, you can continue doing your gesture, but you don't want to do it before we see this output. So let me try backwards. And then that's our predicted class. Then we see do gesture again. And then I'm going to try like right tilting it. And then that should be our predicted class. Okay. Sorry, it was accidentally triggered, but let me just try again for like forward. And then it should just predict that. And I'll go backwards, and that should predict that as well. Let me just reset this. Okay, yeah. If anyone has like any questions, like please like let me know in the chat. So like, yeah, this is this introduction to gesture recognition using like a very basic IMU. You don't really need to buy like a bunch of like fancy equipment, I guess. And like, this isn't like the perfect model. Like I just kind of picked the random forest classifier. So there must be like a bunch of like other ones you can play around with, tune the parameters and so on. And so if anyone needs help, like let me know. And then I'll stop sharing right now.
All right, cool.
And
so yeah, for anybody who's doing this asynchronously as well, of course, feel free to reach out to Jackie or I if you're having trouble finding files or anything like that. And then other than that, I think we can stop recording.
Awesome. Thank you everyone for coming to